And we're live. Okay. Excellent. So, acids and bases. Um, I talked about this a little bit, but acids have acidic protons. They ionize. Okay? So, generally, you have an acidic proton, a hydrogen, paired with something that would ordinarily be a monatomic or polyatomic anion. So, when you put them in water, they dissolve. You get the acidic proton floating free and the anion floating free. That's how we generally write it. But what is actually happening is this guy down here, because you don't get a free proton just running around all by itself. Instead, you have the acid reacting with the water it is now dissolved in, and it transfers that acidic proton over to the water to make hydronium, H3O+. And then you have the anion floating free. So the way we generalize and talk about acids is that they are proton donors. Okay? They donate a proton to something that is acting as a base. So here you have your acid, and here you have your base. Bases are the opposite. Now, the old version of how we thought about them, the Arrhenius system, we thought of them as hydroxide donors because he was familiar with these hydroxide salts that you dissolve them in water, they produce OH minus. But there were a lot of things that acted as bases. They were indubitably, undoubtedly, absolutely, they acted as bases. They reacted with water in the way that bases do. They reacted with acids the way that bases do. Everything about them said acid, or sorry, everything about them said base, except they didn't have hydroxides in them. So the new version, the Bronsted-Lowry system, says that bases are proton acceptors. Okay? Where an acid is a proton donor, a base is a proton acceptor. So here we have ammonia, okay, the biggest example. It reacts with water when you dissolve it to make ammonium. It's taken that acidic proton away from water, and now you have hydroxide in solution. And notice that we have sort of reversed the roles. Ammonia is now acting as a base by accepting a proton, but water is now acting as an acid to donate a proton. That's a thing that can happen. You can have something that can act as an acid or a base depending on the circumstances. So here we have water doing both. We have H3O plus donating a proton to OH minus to make water. Okay? So this guy is our acid, this guy is our base, and this is the result. So to reiterate, strong and weak acids. A strong acid ionizes 100%. Okay, when you mix it with water, the reaction. This reaction is goes 100% all the way to the far end. Every single bit of hydrogen chloride breaks up into H plus and Cl minus. Technically, it reacts with water to make hydronium and Cl minus, but whatever. Likewise, sulfuric acid, H2SO4, completely breaks up into H plus and HSO4 1 minus. Note that only the first proton of the sulfuric acid is strong. The second one is weak. So weak acids don't go completely all the way to the far end to produce their products. Hence, we use these double arrows. Okay? One arrow pointing right, one arrow pointing left, to say that this reaction starts and you build up more and more of your product, but then eventually the products start reacting with one another to go back and make the reactants. Okay? This is called an equilibrium, and we'll talk about them a lot more in the second semester. So what happens is you have some amount of the products, you also have some amount of your reactants, and they exist at the same time. So you don't get 100% over here on the product side. You end up somewhere in the middle. So that's what makes them weak acids. So acetic acid, vinegar, is a weak acid. It only ionizes about 5% in solution. Hydrogen sulfate, HSO4 1 minus, bisulfate, is also a weak acid. H plus and SO4 2 minus are the products, but it doesn't go 100% over here to the product side. It ionizes, I think, about 10%. Okay. So a strong acid, 100% ionization. Weak acids, usually way, way less than that. Okay. So remember, strong acids are strong electrolytes. Weak acids are weak electrolytes. So here's your list of your strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, then nitric acid, chloric acid, perchloric acid, and sulfuric acid. Weak acids, every other acid is a weak acid, so every other acid is a weak electrolyte. Now, I've already touched on this a bit. There's things called polyprotic acids. Okay? A monoprotic acid only has one acidic proton. Polyprotic acids have multiple acidic protons. So HCl, HBr, HNO3, those guys only have the one hydrogen to lose. But H2SO4, it has two acidic protons. The first one is strong, the second one is weak. Phosphoric acid, H3PO4, is a triprotic acid. It has three acidic protons. They're all weak, by the way. So when you have multiple acidic protons, you can get multiple ionizations. So H2SO4 plus water, you get bisulfate and hydronium. And this reaction, about 100% because it's a strong acid. But HSO4 1-, it reacts with water to produce sulfate in solution and hydronium, but it only does that about 10%. 90% of it stays as bisulfate. Phosphoric acid reacts with water to make dihydrogen phosphate and hydronium, only about 5%. Dihydrogen phosphate, it can do that again to make hydrogen phosphate, and that is like 0.005%. It's incredibly weak. And then the hydrogen phosphate can do it a third time to make just free-floating phosphate and hydronium, and that is just ridiculously weak. It barely happens at all. So strong acids, 100%, break up into their ions. Weak acids, far less. So here's the wonderful thing. Acids have their own naming convention. You've already seen me shout out some of their names. When you have that acidic proton and it's dissolved in water, then we name it as an acid. So if your acidic proton is paired with a monatomic ion, then it's hydroelement ic acid. So when we pair with the chloride, then it becomes hydrochloric acid. If we pair it with sulfide, S2-, then it becomes hydrosulfuric acid. Note, hydrosulfuric acid is different from sulfuric acid. Sulfuric acid is when it's paired with SO4, 2-. Hydrosulfuric acid is because it's with that monatomic ion. So hydro means monatomic. Monatomic means hydro. If it's a polyatomic ion, there's no hydro. Instead, it depends on the ending of that polyatomic ion. If it ends with ITE, then it becomes us acid. If it ends in ATE, it becomes an ic acid. So H2SO3, this is the sulfite ion. So we call that sulfurous acid. HClO, this is hypochlorite. So it becomes hypochlorous acid. ATE, this becomes ic, so phosphate becomes phosphoric acid. Note, yes, it's a little bit inconsistent. It's not phosphic acid, it's phosphoric acid. This is perbromate, so it becomes perbromic acid. So this is another set of names for you to learn how to deal with. Fortunately, you're already familiar with the polyatomic ions, so this is not going to be too difficult, I hope. The other thing is note that the number of hydrogens depends on the charge on the ion. So hypochlorite has a 1- charge, so it's a monoprotic acid. Sulfite has a 2- charge, so it's a diprotic acid. It has two of those protons. Okay. Phosphate has a 3- charge, so it has 3 acidic protons. That's why it's a triprotic acid. Likewise, sulfide is 2-, so 2 protons. Chloride is 1-, so 1 proton. All right, so here is some naming practice for you. Go from name to formula, formula to name for all of these guys. I will not be writing these down because there's a lot of them. Yes, I will. Gosh darn it. Okay, so pause it, come back, and you get to see me write all this crap down. All right, welcome back. So, hydrobromic acid. Hydrobromic acid. So hydro means it is paired with the monatomic ion. Bromic means it's with bromine. So this is Br, bromide. Bromide takes a 1 minus charge, so only 1 proton. Chloric acid, no hydro, so this is a polyatomic ion. Ic means it ends in 8, so we're looking at chlorate. Okay? So remember, for those guys, you have a series of 4. Okay. Hypochlorite, chlorite, chlorate, perchlorate. Okay, so each one of them has a 1 minus charge. So chloric acid, Ic, means 8, so it's ClO3. It has a 1 minus charge, so monoprotic acid. Sulfuric acid. Once again, this is a little inconsistent. We are gifted by history with oddities like this. Sulfuric, you would be tempted to say it's sulfurate, but no, it's just sulfate, SO4. So sulfate has a 2 minus charge, so H2. Murray was a chemist. Murray is no more, for what he thought was H2O was H2SO4. All right, so be aware of sulfuric acid and phosphoric acid. Also sulfurous acid and phosphorus acid. They have the in the name, even though it's not in the name of the polyatomic ion. Sulfate, phosphate, sulfite, phosphite. All right, next up is nitrous acid. Us, again, no hydro, so it's polyatomic ion. Us means ite, so that is nitrite. So NO2, 1 minus. 1 minus means there's only 1 hydrogen. Carbonic acid. Again, no hydro. Carbonic means that it is made using the ion carbonate. Carbonate is CO3, has a 2 minus charge, so H2CO3. That is carbonic acid. That is what's responsible for the fizziness of your soda. It's also responsible for the increasing acidification of the oceans. The pH of the oceans is going down, and it's not good because we're pumping CO2. All right, hydroiodic acid. Finally, a hydroiodic acid. The hydro means it's paired with an element. Iodic means it's paired with iodine. Iodide has a 1 minus charge, so monoprotic. Phosphorus acid. Okay. Again, no hydro, so it's with a polyatomic ion. Phosphorus means it's with phosphite, not phosphorite. Yeah, PO3. 3 minus means it's H3PO3. And finally, carbonous acid. Again, polyatomic ion. Carbonous means that the ion is carbonite, so CO2. 2 minus means H2CO2. And this, by the way, is how I know some of you cheat on homework assignments. Well, not in this case, but at a previous school. A lot of people looked at this, and I could tell that they were putting this into the Google box because I got some outlandish responses. All right, let's move on. Go formula to name. Oh, this one, you can still see it over on the right-hand side of the screen. So I'm just going to work my way down. HIO, let's see, I'll need to move my keyboard. I could rearrange the camera, but that's difficult. So, HIO4, well, it's with a polyatomic ion. Specifically, it's with it's with periodate. So that means that it becomes periodic acid. I learned not to put those on tests because people said, "What the hell is a periodic acid?" All right, this next one, it is with chlorite. It's polyatomic ion, so it is just going to become chlorous acid. H2C2O4, you'd probably have to look this one up. That is the polyatomic ion oxalate. It ends in 8, so it becomes oxalic acid. Now we have a monatomic ion, so hydro It's specifically paired with fluorine, so fluoride, hydrofluoric acid. That is what they use to etch glass. It's one of the few acids that will dissolve glass. Here we have hydrogen paired with a polyatomic ion again. Specifically, it's paired with nitrate, so that is nitric acid. Next, HBrO, that is hypobromite, so hypobromous acid. IO2, that is iodite, so iodous acid. And finally, HC2H3O2, that is acetate, so it becomes acetic acid, or vinegar. All right, so that is all the names to formulas and formulas to names. And that will do it for, whoa, what the, oh, yes. Strong and weak bases. I was ready to be done. Okay, a strong base is any highly soluble hydroxide salt. Okay, so that means, once again, popping over to the periodic table, all of our alkali metals, those will make a strong base paired with a single hydroxide, but only calcium, strontium, and barium, the heavy alkaline earth metals, will only those three make a strong base. Okay, beryllium and magnesium don't. That's because they're not soluble in water. The rest of them are insoluble, so they're not good as strong bases. It's just that they don't dissolve much in water, so they don't produce much hydroxide. So your weak bases are all your other insoluble hydroxides, also all of your covalent bases, your covalent compounds, molecular compounds. So those are usually the amines. They usually have a nitrogen in them, like I said in an earlier lecture. So, as for being electrolytes, your soluble ionic bases, the strong bases, those are going to be strong electrolytes. All of your covalent compounds are going to be weak electrolytes. Personally, I've seen it written both ways when it comes to the insoluble compounds. They dissociate 100% when they dissolve. It's just that they don't dissolve very much. So do they count as strong or do they count as weak? It's kind of up in the air. So that's that. Now, there's no new set of names for this. Your bases are either ionic compounds, which already have a perfectly kosher naming system that you already know, or they're covalent compounds, which again have a naming system that you don't know and you're not going to learn, because most of them are organic compounds. The one you do have to really know is ammonia. Ammonia is a weak base. All right. Now that does it for this set of slides. Oh, there's only one more. I'll go ahead. I will see you in a few minutes for neutralization reactions.